Alright, so let's look at the second of the two examples. And this is a cylinder problem, which means that we're going to be looking at the second set of Heisler charts. So remember, it's plates first, then the cylinders, and then finally the spheres. Okay? In this case, I've got a cylinder of 10 centimeters in length and 10 centimeter diameter. This may not be the best choice for this form of calculation. We might find that if we were to repeat this and do it using the lumped capacity method, we may get as effective of results, because here, by this being so short, this method doesn't take into account end effects, so the heat losses out of the end are being neglected, and in this case that's actually fairly significant. But we're going to do it by this method because that was what was suggested in the book that I had borrowed this from. Again, it's not really a perfect solution. But if we go through and do this, the given information, it's initially at 300 C, it's immersed in something at 40, and with this H value of 280, and we want to know what's the temperature at the center of the solid when T is 2 minutes. And we're also going to want to find out what the heat loss is. So to solve this, first of all, I need to do a little bit of modifying of the data to get started. First of all, like with the plate, I don't want to know the distance from edge to edge. I want to know the distance from the center to the edge. So that's the radius. So I'll take the diameter and divide by 2. And just always be sure you're doing that, whether it's a cylinder or a sphere or a plate, that you're always looking at the distance from the middle to the edge. Okay? The other thing is my time is 2 minutes is fine. I certainly, have a gut feel for how long 2 minutes is, but all my units are in watts and joules, and so I really need to convert that over to seconds, or my units are not going to cancel. So let's take that and convert my time to seconds. Okay? So if you get started in the right units, then it's going to make it all a little more seamless as you go through and do the calculations. Now in this case, we are again looking at chart 1 because I'm trying to figure out the temperature of the center, and temperature of the center is chart 1. Okay? So this case I have time, which is basically the Fourier number. Okay? So alpha t over L squared, and I've got all of that information, or alpha t over R squared. I've got all that information, so I'll be able to find a value along here. I have K, H, and R, so I can find 1 over my bio number. And then I'll be able to use that to calculate my theta ratio. And the theta ratio is going to have hidden inside there the temperature at the center. So this should be a fairly straightforward problem. I just need to calculate this value, and then come over to my graph. Okay, so 1 over BI is K over HR. So in this particular case, K over my H over my R. Should be a dimensionless quantity there, so I don't need to worry with my units if I made sure that everything cancels. And then I'm going to have the Fourier number, which is alpha t over R squared. Okay, so in this case, alpha, my time in seconds, over the radius squared, or divide by the radius twice. Okay, so I get that from my Fourier number. So if I come over to my graph then, I have 1 over BI is 0.87, so I've got 0.8 and 1, and so let me draw a line on there for that. Okay, so 0.8 to 1, so that's about 2/3 of the way through. So, well, 1/3 from 0.8. Okay, so somewhere in there. And the Fourier value is 0.17. So I come down here, and what I see is that 0.17 is going to fall into this little area over here. And when I come up, I didn't draw that very straight, but regardless, what you're going to see is it falls into this little scrunchy area. And that's why we have the second graph. So the second graph, that's a duplicate of information, but it covers this little area where it's impossible to read. So let's go get the other graph. So here it is. I'll drag it over so that we can be looking at it. You see that it is basically the same graph. Okay, so I'm going to move my 1 over BI line over, if I can pick it up. Okay, so 0.87, so roughly 2/3 of the way from 0.5 to 1. Apparently I'm no good at moving the ends of my graphs. So about 2/3 of the way over. Let me catch the top up here and move it. So roughly 2/3 of the way over. Okay, and then I need 0.17, so let me bring this graph over here. So that looks like about 0.17. Stretching this on up so that I get the intersection. From there, go straight across. Well, it looks to me like about 0.89. Okay, so the theta naught over theta I is 0.89. Go ahead and convert these over so that they look like thetas. Alright, so there I've got my theta naught over theta I. I actually have theta I information there, right? So theta I, in this case, is just the temperature difference at the beginning. Okay, so it's this minus this, or 260 degrees. Okay, so that means that theta naught, just using algebra therefore, okay, is going to be this times this. Okay, okay, 231 degrees. And that then converts over to T at the center. Okay, T at the center is this number and then add back in T infinity. Okay, so 271.4 degrees C after 2 minutes. So it started out at 300, it's cooled off 30 degrees. That seems like a reasonable value for metal. Okay, so that was part 1. Part 2 is how much heat is going to be lost in this time. So this allows us to use chart 3. So chart 3 is this one. So it looks like all these sweeping S-curves. Okay. As you're looking at this one here, it's got the bio number squared times the Fourier number, and then these are BI, not 1 over BI. Okay, so really all I have to do is I've got the information. I'm just going to kind of modify it a little bit. So now I need to calculate BI, which is fortunately just 1 over the value I had before. Okay, I'm going to need that quantity squared times my Fourier number that I've already got. Okay, so that number squared times my Fourier number. Okay, so 0.22 and 1.15. So I'm going to come find those on this curve. So 1.15 is going to be right in here. Okay, 0.22. Okay, so this is 0.1, 0.2, 0.4. So 0.22 is right in here. Let me draw that in as a straight line. So 0.1, 0.2, 2.2, somewhere right in here. Because it's easiest for me to do straight lines, I'm not going to try and draw in the entire curve. I'm only going to draw in the portion that we're really interested in. But remember, BI is now 1.15. So there's 1.15. I'm looking at something 15% of the way between those two, so kind of right in there. And taking that intersection and going straight across. Okay, looks like it's about 0.26. Okay, so that's 0.26. And so now I need to calculate Q max. Now, these are the formulas that are not in the data booklet, so you want to write these in. And for every shape, they're a little different. You can get it from the notes, you can get it from the textbook. But in this particular case, Q max can be calculated pi, rho, gotta slide up there to my rho, okay, times C sub p times my radius squared times my length, and then times my delta t. And this is going to be from the beginning time minus t infinity. Okay, and so that's my Q max is, wow, really large. And this is in joules. If you go through and check all the units, I'm not going to do it in this video, but you should have done it in class, and you should, do this at least once to verify what that is. But this is the total amount of time taken to get to this point, and so that's in joules. It is not a rate of heat transfer. And so Q is going to be this Q max times my 0.26. Okay, and again, that's joules. If I wanted to look at it in, say, kilojoules, which might be a little more reasonable quantity in this case. Okay, so 187 kilojoules of heat are required to do that much cooling. Okay, if you are using signs, okay, this is heat loss, the object is cooling, so this is a negative quantity. You can either choose to call it negative, or you can say it's 187 kilojoules of heat loss from the object. Okay, so either words or the other. So this concludes the two examples. If you're still having problems, stop by for office hours.